All right. Last hour, we showed that if a square matrix has an inverse, then it is unique, right? There's only one. And therefore, we can give a special notation for that. Okay? We have seen that the square matrix, the square matrix is an inverse, then it is unique. Okay. So we can say that the inverse of A, right? I can just call it that inverse, the inverse of A. Therefore, we may call the inverse matrix the inverse of A, the inverse of A, and denoted as A inverse. Okay. Since there is only one, I can call it the inverse of A, and we will use this notation, A inverse. So this corresponds to a unique matrix. If I had different inverses, then I wouldn't be able to use, I couldn't use this notation because this one refers to which inverse, right? G or C or D. But since it is unique, I can call it like this, the inverse of it. Tamam mı? All right. Okay. There are some exercises. Maybe you know. Exercises 1. Assume that is this 2 by 2 matrix W X Y Z. It is 2 by 2 matrix. So that W Z minus XY is not 0. Okay, this product and this term is not 0. Product of the diagonal entries minus the off diagonal ones is not 0. Then A inverse is equal to the following: 1 over W Z minus X times Y, Z minus X minus Y, W. So A inverse is this matrix. We have this real number multiplied with this. Multiplication of a matrix with a real number is just, you just multiply each entry. So this entry is multiplied with each of these, and we claim that this is the inverse of A. Okay. So what is the inverse then? You do the following. You interchange the diagonal entries, right? W and Z are interchanged, and the off diagonal entries X and Y are replaced by their additive inverses, minus X and minus Y. So this is the claim. How can you prove this? Well, you just multiply and see if the product is identical, right? That's the definition of being inverse. If this is the inverse, then A times A inverse should be identical. So, efendim? Sonucu kullanarak proof'tan ne kastediyorsun?
Yani eski yaptığımız şeyden sonra elde ettiğimiz sonucu onu anlatır mı?
Tam anlamadım ne demek istediğini.
Yani bunları en sonunda sizin benden sonra söylediğiniz kısmı kanıtlamak istiyoruz yani.
Hı?
Onu kullanıp yeniden aydan geçtiğimiz zaman kanıtlamak istediğimiz şeyi kanıtla kullanabiliyor muyuz?
Kanıtlamak istediğiniz şeyi kullanıp yok o olmaz. Yani bilmiyorsun ki onu. Tersini yapabilirsin. Kanıtlamak istediğin şeyin tersini kabul edip çelişkiye varırsan tamam ama öbür türlü bir ispat yöntemi yok. Çünkü kanıtlamak istediğini kabul edersen zaten ispat bitti demektir. Değil mi? Hani. Oradan evet. We use the definition. What is the meaning of inverse? If this is the inverse, then this matrix times this matrix should be identity, right? So you must check A times A inverse is identity and A inverse times A is identity. Actually, one should say this. You know, one should call this B, and then A times B and B times A is identity. Then this B will be A inverse. Okay, but you know, we can just skip that. Let's see if this is true. So, A times or A inverse times alpha. So what is A inverse? A inverse is this real number times this matrix Z minus X minus Y W and then A. A is just X, Y, Z, W. No, W. Sorry. W, X, Y, Z. Okay, let's see what we get. Z times W minus XY. Z times W minus XY. This is the first entry. And then Z times X minus Z times X. Z times X minus X times Z. Minus YW plus YW minus XY plus WZ. Well, this is just ZW minus XY. This is just 0, another 0, and then WZ minus XY. Well, this is the same thing as this one, right? WZ minus XY. When you multiply this matrix with this coefficient, you just multiply each entry. And we know that this is not 0. That's why, you know, I can write it this way. Otherwise, I couldn't write this. Now, this time, this is just 1, 0, 0, 1. So this product is identity. And then also one must check that A times A inverse is identity. Okay, just similar computation. You just interchange these two. So this gadget satisfies both equalities. This product is identity and this product is identity, right? So And A inverse is just whatever written over there. So WZ minus XY, Z minus X minus Y W. Okay. Tamam mı? If you are not sure what to write, I mean, if you are asked to prove something or show something, compute something, and if you are not sure what to do, you should remember the definitions. I mean, if you are asked to find out, for example, the inverse, you should remember what was the inverse, right? Or if you are asked to prove something relating the inverse, then you should remember its definition. What was the inverse? Okay. Okay, so a numerical example is this. Let A, for example, be this matrix 1, 1, 0, 2. Then its inverse. Inverse is what?
-1.
1 over the product of these two, 1 times 2 minus 0 times 1, and then what we do?
2 minus 1.
2 minus 1, 0, 1, right? You interchange these two, multiply these two by -1, and you write here the product of the diagonal ones minus the product of diagonal ones. So this is just 1 over 2 times this matrix. So I can write it this way: 1 minus 1 over 2, 0, 1 over 2. So the inverse is this. Okay. Evet, ama burada işte bu determinant 0 değilse yazabiliyorsan var zaten. But here we show that if this is not 0, then it is an inverse. So if this is not 0, kim sordu? Oh, pardon. So if this is not 0, then it is an inverse. Kontrol etmeden yaparsanız tabii ne başınıza gelebilir, bulamayabilirsiniz. Çünkü yoksa bulamazsınız, değil mi? O zaman böyle bir bakarsınız, belki de yoktur diye. Okay. Another exercise. Show that inverse of A times B is B inverse times A inverse, provided that both A and B are invertible. Both A inverse. And need the arguments. Here we claim actually two things. If A and B are matrices that have inverses, then their product is also inverse, and that inverse is nothing but this matrix. How can we prove this? Well, we are claiming that A times B has an inverse, and this is the inverse. So you just apply the definition of being inverse. If this is the inverse, then A times B times this matrix should be identity. So we just check this: A times B times B inverse A inverse, right? We claim that this is the inverse. Let's see if it is the inverse. Since product is associative, I can put the parentheses in any way I want, so I can just do this. Right? Now B times B inverse. I assume that B has an inverse, right? And it is, and I use it here. So this is just the identity matrix. Well, since this is identity, this product is just A inverse, but A times A inverse is also identity. Yes. Are we done? No, we have to also show the other way around, right? B inverse times A inverse times A times B. What is this? This is just B inverse A inverse A B. B inverse. This is just identity. And this is just B, and this is also identity. So this matrix has an inverse, and this inverse is this one, because if it has an inverse, then it is unique, and this satisfies the conditions of being an inverse. Therefore, this is the inverse of A times B. So hence, A times B is an inverse, and that inverse is nothing but B inverse times A inverse. Okay. Okay, I'll leave this exercise to you. Identity plus B times A inverse is just A inverse times identity plus A times B inverse and A. Provided that all inverses in the expression exist. Yani bu inverse varsa, bu inverse varsa ve bu inverse varsa bunlar birbirine eşit. Like if all the inverses appearing in the expression exist, then we have this. Okay, I will leave this as an exercise to you. All right, what else? Okay, determinants. We will later spend a lot of time on determinants also, but now just at least for 2 by 2 and 3 by 3 matrices, we will see what's the determinant. So determinant of a square matrix is a real number, is a number, not necessarily real, is a number. Having some geometry, meaning we will study later. For the time being, we will just give formulas, okay? We have formulas for the determinant. Of matrices. Okay, let's see those formulas. Later, as I said, we will spend a lot of time on determinants and understand what why they are important and what are their geometric meaning. So we will denote determinant of a matrix like this, determinant of A. In case, for example, A is a 2 by 2 matrix like this one, A, B, C, D. Determinant is just actually the expression we have seen over here. Okay, product of the regular ones, AD minus BC. Okay. So inverse is then what? 1 over the determinant times this matrix, right? In particular, a 2 by 2 matrix as an inverse. If and only if its determinant is non-zero. Like we have seen here that if this expression is not zero, then it has an inverse. And the inverse is given by that formula. For example, determinant of 2, 3, 4, 5 is what? It is 8 minus 15, right? 8 minus 15, so it's minus 7. Okay. And let me tell you what is the geometric meaning right away. You can check this actually. You write the following two vectors in the plane. 2, 3. So 2, 3. 2, 3. And 5, 4. 5 and 4. It is this vector. And then you complete this to a parallelogram. How do you do this? You write, you draw parallel lines to this. Starting from this point, you draw this line. So you get this, and then you have this. So you get a parallelogram. So this vector is the same as this one, and this vector is the same as this one. You obtain a parallelogram, and the area of this, okay, the area here is area is of course a positive number. It is the absolute value of this determinant. So that's the geometric meaning, but later we will study this in more detail. Okay. And this is the reason why the determinant is something important. So it is not just an algebraic expression. Okay? Well, it is, but I mean, it is a meaning. Since I am a topologist and geometer, when I say it has a meaning, it means it has a geometric meaning, okay? Or topological meaning. Otherwise, I don't call it meaning. Okay, determinant of what about 3 by 3 matrix? A, B, C, P, Q, R, X, Y, Z. What is the determinant of this? Well, again, it's an expression which you cannot keep in mind, but I'll write, once. A Q Z plus B R X plus C P Y minus B P Z minus C P X minus A R Y. Okay. Later, we will see methods, and this expression will be a lot more meaningful. Okay. Again, this corresponds to a geometric object. This is the two-dimensional determinant is area, three-dimensional determinant is volume. Okay, and so on. Four-dimensional volume, fifth dimension, five-dimensional volume, and so on. After three, we call all of them volume. Dimension one is length, dimension two, in dimension two it is area, in dimension three it is volume, 4, 5, 6, we just call it volume. Yes. Inversion olması için determinantın sıfır olması mı? Güzel soru. Hepsi için geçerli. Bunu yazayım. We will see later. Square matrix. Square n by n matrix. As an inverse. If and only each determinant is non-zero. Okay. Now let's see. How one can define determinants of bigger matrices. All we have to do is to keep the determinant of actually 2 by 2 matrix. Then algorithmically you can obtain all the determinants of matrices of any size. How? Here is what we do. That's called Laplace expansion. Let A be an n by n matrix. For any ij between 1 and n, the ij minor denoted as nij is the matrix, is the determinant of the n by n minus 1 times n minus 1 square matrix obtained from A by deleting the ith row and jth column. Then we can define determinant of A inductively as şöyle determinant of A parantez almış biz de öyle yapalım. Yani to define the determinant of a 3 by 3 matrix, we use determinant of 2 by 2 matrices. To define the determinant of a 4 by 4 matrices, we use the determinants of 3 by 3 matrices, which are obtained from determinants of 2 by 2 matrices. So once you know determine how to compute the determinant of 2 by 2 matrix, you can define the determinants of any square matrix. And here is the formula, how we define it. I from 1 up to n minus 1 to the power. Here I have I minus 1 and then 1i and then n 1i. So, okay, now let's see what does this mean. And we will explain this formula also, okay? Let's do on an example. So let's say A is this. ABC. Okay. PQR XYZ. But I can, use also the following notation so that I'll get something compatible with this one. So this is A11, A12, A13, A21, A22, A23, A31, A32, and A33. Okay. Now, what are the minors? For example, what is M11? What is the definition? This is the determinant of the matrix obtained from A by deleting the first row and first column. So I delete the first row and first column. Whatever is left, well, what is left? 2 by 2 matrix. The determinant of this is the minor M11. So this is just the determinant of A22, A23, A32, and A33. Or if I write it in this, representation, it will just Q, R, Y, Z, right? Q, R, Y, Z. And what is the determinant of this one? Well, this is just diagonal ones minus off diagonal ones. All right. Which other minors do I need? I need M11, M12, and M13. So, what about M12? Well, that's the determinant of what? This time, I delete the first row, but the second column. What is left? A21, A23, A31, and A33. Or determinant of ne yaptık? Şunu ve şunu yok ettik. Ne kaldı? P, R, X, Z. So what is the determinant? P, Z minus R, X. All right. And finally, M13, that's the determinant of what? You delete the first row and the third column. What is left? 21, 22, 31, and 32. Or this one here, PQXY, PQX and Y. So this is P times Y minus Q times X. All right, now I can write down the determinant of the 3 by 3 matrix. Let's see. Okay. So determinant of the 3 by 3 matrix A, B, C, P, Q, R, X, Y, Z is what? Well, this is the formula. So I from 1 up to N. N is just 3. A, 1, I, M, 1, I. So this is just A11, M11. No, I forgot the minus sign here. Minus 1 to the power, I minus 1. Then I equals 1, I get 1 minus 1, which is 0. Minus 1 to the power 0 is just 1. So sign here is 1, A11 times M11. And then for I equals 2, minus 1 to the power 2 minus 1, which is 1. So minus 1 to the power 1 is minus 1. So this sign should be minus. And then I have A1, 2, M1, 2. And then I equals 3. When I equals 3, I get minus 1 to the power 2, which is plus 1. A1, 3, M1, 3. And then I just plug everything. A11, first entry here, which is just A, times M11. We just computed that. M11 was what? QZ minus RY. QZ minus RY. Minus A12. A12 is this element. B times M12. M12 PZ minus RX. PZ minus RX. Plus A13, which is just C times M13 PY minus QX. PY minus QX. So let's see what we have. AQZ plus BPZ plus EPY minus ARY minus yok ters yaptım. Pardon. I'm sorry. Okay. Plus ones are AQZ and then BRX, right? And then EPY minus ones are ARY minus BPZ minus CQX. Are they the same? AQZ, yes, BRX, CPY, RAY, BPZ, CQX. Okay, they are the same. Tamam mı? And from this, you can compute the determinant of a 4x4 matrix, 5x5 matrix. Of course, what you get is a total mass, right? I mean, it's very complicated formulas. But as I said, they have geometric meaning. And once you know the geometric meaning, you will feel much comfortable playing with all these. However, you know, these algebraic expressions, these expansions and so on have also theoretical applications, okay? Although they look very technical and doesn't have much idea in them, it's not like that. These expressions, you know, this formalism has also some, theoretical application. Linear algebra is, I guess, you know, together with calculus is the, most important part of mathematics in both mathematics and in all the other sciences. Most of the, mathematics used in other sciences like physics or engineering is basically calculus and linear algebra, and maybe their higher versions. But linear algebra is certainly very important. Okay, what else? Okay, there's only one last thing. I have, okay, 5 minutes is enough. And then we will be done with this next thing, okay? This is a topic in linear algebra. Unfortunately, it is not covered in many, in any course. Either you don't have time for this, or people think that it is more advanced, so it is always delayed, and it happens sometimes that we never teach this in undergraduate level. But this book gives a lot of importance to tensor products, and you will see why at the end. But for today, I'll just give you what we mean by tensor product. in the in a specific way for specific matrices. First, if I have a matrix like this, let's say a 2 by 2 matrix or n by n matrix, we define transpose of A, and it is nothing but the following. You just take each row and write as a column. So you take this row, okay, write as a column, A, B, C, and then you take the second row and write as a column. Now this was 2 by 3, now it is 3 by 3. Okay? Transpose of A. A very geometric operation, right? You just take it and put it upside down. Bu aslında şeyi gösteriyor değil mi? Mesela niye 2 çarpı 3 çarpı 2 right? This proves why 2 times 3 is 3 times 2. Why is that? Well, I have 1 3, another 3, so we may regard this as 2 times 3, right? You just make it upside down, the same figure, the elements doesn't change, but now we have 2, 2, 2, we have 3 times 2. Right? So you can do this, of course, for m and n. So you get n times n equals n times n. The geometry. Okay, what about the tensor product? If Q and R are matrices like this, let's say it is this one, and R is this one, A, B, C, we define tensor product of these two is this product. So I take Q, pardon. Yo. Okay. A, B, C. Q, A, B, C. Pardon, should Q, Q, R. Q times R. Yani şöyle diyeyim. Yanlış yazmış sanırım da. R transpose R transpose Q. What is R transpose? X, Y, Z. Q is A, B, C. So this is a 3 by 1 matrix. This is a 1 by 3 matrix. The result is 3 by 3, right? 3 by 3. And what is this? You just take each element and multiply each of these. So x times A, x times B, x times C, y times A, y times B, y times C, z times A, z times B, z times C. Okay, this is the tensor product. Okay. Efendim? Yok. Tabii ki. Evet. So this is not just for three, I mean, for this side, we can just take this for any size it works. Thank you.